Alright, we are going to look at a review of arithmetic and geometric sequences. Let me make sure the lighting is, that's a little better. Okay, so an arithmetic sequence is when one term to the next by always adding the same value, or you could subtract, but we're just going to look at adding. And so this is also forms a linear function. A geometric sequence goes from one term to the next by always multiplying, or dividing, or multiplying by a fraction, which would be the same as dividing, by the same value. And this forms an exponential function. Okay, so what we want to do is for each of the following sequences, determine if the sequence is arithmetic, geometric, or neither. If it's arithmetic or geometric, we want to write a formula for the sequence. Okay, so the way to think of these is, let's think of this as being the output of some function, and this is the input. So we like to start at 0. So just think of, if you want to think of this as input-output, think of this as the 0 term, first term, second term, third term, fourth term, fifth term, sixth, etc. So think of these as the inputs, and this is the output. Now in this first one, each time do we go up by adding a certain amount or by multiplying by a certain amount? So let's see. If we go from 2 to 6, we add 4. If we add 4 again, no, we would have 10. So we can already tell it's not arithmetic. Okay, so let's see, is it geometric? Well, to get from 2 to 6, we multiply by 3 times 3. And then to get from 6 to 18, hey, we times 3 again. And then to get from 18 to 54, we multiply by 3 again. And that keeps going. If you keep multiplying by 3, you get the next term. So this one is geometric. Okay, but now how do we get a formula for this? So again, the best what to do is to think about this as being input-output. So maybe let's make a little table. So I'll make a table over here. So we'll think of this as being the in and the out. So we've got 0, 1, 2, 3, 4, going down. So we start at 2, and then to get the 6, that's actually 2 times 3. Okay, and then the next one is the previous one, which is 2 times 3, and then we times 3 again. Okay, and then the next one would be 2 times 3 times 3 times 3. But we know that an easier way to write 3 times 3 times 3 is 3 to the third power. Okay, and so now hopefully we can see the pattern. So the next one would be 2 times 3 to the fourth power. And so the next one would be 2 times 3 to the fifth power. So it's this exponent that's changing. Like for example, up here, this is the same as 2 to the 0 power. This is the same as, 2 times 3 to the 0 power. This would be 2 times 3 to the first power. Sorry, this is getting kind of crunchy in here. This is 2 times 3 squared. So down here, if whatever our input is, let's call it capital N, our output will be 2 times 3 to the n power. So that's our formula, 2 times 3 to the n power. And you can also just look at this as this is our initial value, and that's this number here. And this number here is our multiplier. Okay, so there's our formula for that. So let's look at the next one. So going from 5 to 20, well, let's see, we can times by 4. Then if we times that by 4, well, no, that's not going to work. We'd have 100. So we already can see it's not geometric. Let's see, is it arithmetic? So let's see, we add 15, and then we add 15. Okay, and then we add 15. Oh boy. Add 15. Okay, so if it's arithmetic, it means we're going to add 15 each time, which works from here to here and here to here, but here to here it doesn't work. So we can tell right away this is neither geometric or arithmetic. All right, let's take a look at this third one down, C. We're going 5, 12, 19, 20. Okay, so let's first try to see maybe it's arithmetic. So we add 7. That means we'd have to add 7 each time. Add 7. Add 7. Okay, so this one is going to be arithmetic by adding 7 each time. Now, again, we could do the same thing that we did before by making a table. So yeah, let's go ahead and do that. So I'll make it over here. I can make it a little bigger. We got our in and our out. So again, let's think of this as the 0th term, 1st term, 2nd term, 3rd term, etc. So think of the term number is the input, and the output will be the 5, 12, etc. But let's think of the 5 as being 5 plus 7. Okay, and then what do we do again? We've got to add another 7. So we've got 5 plus, and now we're adding 2 7s. Let me rewrite that as 7 times 2. Okay, to get the third term, it's going to be 5 plus 7 times 3. 5 plus 7 times 4. 5 plus 7 times 5. All right, so suppose we wanted the nth term. Well, notice the thing that is the n over here is what it's getting multiplied by. Over here we could have this as plus 7 times 0, and this could be 7 times 1. It doesn't change them at all. We still want this to equal 12, and this equals 19, and this equals 26, and so on. Okay, so our formula will be 5 plus 7 times n. So it's 5 plus 7n. Okay, and again, we don't have to make that whole table because we know that, and we've seen linear functions come in the form y equals mx plus b. Well, in this case, we've got the mx second, so I'll just put b plus mx. And so in this case, this 5 is your initial value. Right, and we've also seen that as being the y-intercept, or the starting value, and then the 7 is our slope, or the rate of change, or in this case, it's what you add every time. And so this forms a linear equation. If we were to graph it, it would form a straight line. Okay, so we got that one, and now let's take a look at D, and we got, well, what's that? That's the Fibonacci sequence, so that's neither. It's the Fibonacci sequence. And that's the one we saw in class that has all those relationships in nature and all those crazy things with the seashells and all the sunflowers and all that. But hopefully this gives a quick little review on arithmetic and geometric sequences and how you can find their formulas. Rock on.